Ladies and gentlemen, your class recording has started. So, as you can see from the packet today, we are going to get started on section 9.3. Chapter 9 is going to be our next unit, but based on how it was written and looking over it, I think the stuff that's in section 9.1 and 9.2 makes a little bit more sense if we talk about the stuff that's in section 9.3 first. Your author apparently doesn't agree, but you know he's not here teaching you, so I get to teach it, right? But it starts off with, according to Newton's second law, an object moves with a constant speed in a straight line unless acted on by a force. I might argue that we could change one word in that sentence, or maybe we should change one word in that sentence. Anybody have a opinion on what word we might change in that sentence? According to Newton's second law, an object moves at a constant speed in a straight line unless acted on by a force. I would not go with speed.
Unless
Object.
I would change this word. Okay? The idea of an object moving with a constant speed in a straight line unless acted on by a force is what? Inertia, which is Newton's first law.
So did they make a mistake?
No, I mean, you could also argue that it's a second law thing, because you could say that force causes acceleration. If there's no force, there's no acceleration. If I was writing it, I would probably write it as Newton's first law, but that's just kind of semantics.
I don't understand how those can just be interchangeable.
What? Well, they kind of relate to the same idea. Does an object move? Does it not move? But more importantly, based on that idea, this conceptual problem down at the bottom. So it says a puck attached to a string undergoes circular motion on the horizontal surface of a frictionless air table. So it's on basically an air hockey table, right? And it's moving in a circle. And it says if the string breaks at the point indicated in the figure, is the subsequent motion of the puck best described by path A, B, C, or D? So this puck, right, traveling around in a circle in this direction, and then when it gets here, the string breaks. And what we say is it's asking you what's going to happen to the puck at the moment that the string breaks. Which path is it going to take? So the answer to this question is B. Two ways you can answer that question. One, you've already answered this question like 3 times on different tests. Okay? But two, inertia says that things are going to move how? Straight line. Constant velocity, which means same speed, same direction. If the string breaks and there's no friction, because it says it's frictionless, there's nothing to cause that object to change. So at that very moment, the object would move in a straight line path, which is represented by B. That being the case, if we spin an object around in a circle, let's say like this. Nice constant speed, right? Is this object accelerating?
No. Yeah. No. Yes.
Well, constant V, that means
Because it changes direction.
I didn't say constant V.
Isn't that what you just said? Constant speed?
I said constant speed. It's
Oh.
not constant V.
Oh.
Is it so it is
speed,
accelerating?
Yeah.
Why is it accelerating?
Because it's changing directions.
Constantly changing directions, right? So we said that acceleration can take 3 forms: speeding up, slowing down, or changing directions. So in the case of something moving in a circular path, even though it may not speed up or slow down, it is still accelerating. So like it says on your sheet, right? Circular motion requires constant acceleration. So it says, the direction of the car's motion changes continuously, even if its speed remains the same. So if the direction is constantly changing, that object is constantly accelerating. Now, based on that, let's take a look at those 3 pictures that are down at the bottom. All right, here's picture number 1. This figure is showing the path of an object moving in a circle. Let's call it, I don't know, it's a rock. All right, so there's your rock. So the rock is traveling around in a circular path. And at that point, up at the top of the circle, the red vector is representing its velocity. And then, a little while later, the green arrow is representing its velocity at that moment in time. First, did the object speed up or slow down? Based on that picture. Jamie says no. Why not? Okay. Jamie says no. She's right. How can we tell from this picture that this object has not sped up or slowed down? Because the arrows, what do you see about the arrows? They're the same length. But has this object accelerated? Yes, because what do you see about the direction of the two arrows? Okay. Down here, right, this is our equation for acceleration, right? Delta V over delta T, the change in velocity over the change in time. And if we want to know delta V, we go V2 minus V1, right? Or V final minus V initial. Good?
I like the slope of the tangent, right?
Yes. That the velocity is always, the velocity of an object is always tangent to the circle at that point in time. And that's going to be important in a second when we talk about that idea. So hold on to that thought for a second. If it doesn't matter, then if it doesn't make sense, then don't worry about it. But yes, it is tangent. It is tangent to the circle.
Yeah.
All right, I'm going to change the picture, and I'm going to make it look like this. Two changes. First, if we have to take V2 minus V1, can we just take the value of V2 and subtract the value of V1? Is it that easy? Nope, because we got the direction thing, right? So we have to do vector addition in this case. So two things that I changed from the first picture to the second picture. What are the two things that I changed from picture 1 to picture 2? Okay, I changed the direction of vector 1, right?
Yes.
We can also write this as V2 plus negative V1. That's the same thing, right? So, if I have to add negative V1, I gotta flip V1 around. It was originally pointing to the right, now it's pointing to the left. And the second thing that I changed about this picture is what?
The placement of it.
The placement of V1. If we are adding vectors together, remember back in chapter 4, how do they have to be lined up? Head to tail, right? So if I'm doing V2 plus negative V1, V1 has to start where V2 ended, right? And then to find the sum of those two, what do? Well, not yet. If we just have these two, right, we could add components, although we don't really have an x and y here. The actual vector sum is we draw an arrow from the beginning of the first one to the end of the last one, and it looks like that. That yellow arrow represents delta V. Okay?
But then that's a right angle.
Aha. So two things. One, this is a right angle.
Yeah, okay.
Okay.
I get it.
And two, that yellow arrow, even though maybe it's not exact because I drew it on PowerPoint, it is not exactly the radius, but it points towards where?
Oh, the center.
It points towards the center of the circle, right? If a line is perpendicular to the tangent line of a circle, it points towards the center. I know I'm throwing out geometry terms and everything like that.
I don't
But,
even know what you just said.
okay, so,
Perpendicular.
do you know what perpendicular means?
Yeah.
Okay, good.
But still.
So what we find out is that this yellow arrow and this green arrow are perpendicular, okay? Green is representing velocity. Yellow is representing delta V, which we use to calculate what? Acceleration. So green is velocity, and the yellow is indirectly representing acceleration.
Then red's velocity.
Red is the previous velocity, right? But
Previous.
like when
Is you know how-
when this rock was up at the top, right? It's like red represents its velocity when it was here.
So you just moved it?
Well, it's going along the circle, okay? Because remember we said, Sam, that as it moves along that circle, its direction constantly changes, right?
Okay.
So it has different velocities every single time it moves because it has a different direction. What we did here is basically just going through the process of doing delta V over delta T to find the acceleration. But you can't just add or subtract numbers, you also have to do vector addition because they're different directions. And when you do that, you end up with an arrow that points towards the middle of the circle, even though it may not be exact because I didn't draw it exactly, but you end up with a vector that points towards the middle. So, what does that mean? Well, if we go back to chapter 3, if you have velocity in this direction and acceleration in that direction, if we have velocity and acceleration in the same way, physically, what would we see happen to an object? Moving that way, but what would happen to it while it was moving that way? It would speed up, right? So when we have velocity and acceleration in the same direction, it speeds up.
That's
If,
the chart that you gave.
yeah, right, that chart, right? If velocity is in this direction, but acceleration is in that direction, right? If velocity is positive and acceleration is negative, physically, what do we see happen to that object? That one will then slow down. But in this picture right here, I have velocity this way, but acceleration is this way. They're not in the same direction, they're not in opposite directions, they're perpendicular to one another. If when they're in the same direction, an object speeds up, and when they're in opposite directions, the object slows down, if they're perpendicular, constant, not velocity,
Sorry.
it's not going to speed up and it's not going to slow down, but what is it going to do? It's going to change direction. This is acceleration, but it's a specific type of acceleration that we call centripetal acceleration. Centripetal acceleration is not positive acceleration, and it is not negative acceleration. It's different from both of those. Positive acceleration causes an object to speed up. Negative acceleration causes an object to slow down. Centripetal acceleration causes an object to change direction. That's why an object moving in a circle requires a constant acceleration, because it is continuously changing direction. The amount of acceleration, or the magnitude of acceleration, depends on two factors. Here, we see the formula for centripetal acceleration, A sub Cp, acceleration centripetal, is equal to v squared over r, where v represents the speed that that object is going around the circle, and r, not the velocity, the speed, even though it's v, right? Because is the velocity changing? No. Sorry, the velocity is changing, but is the speed changing? It's not going faster or slower, right? It's just changing direction.
Okay.
And then R is the radius, or how sharp of a turn you make. So, a couple of things. One, does anybody have something in their car that hangs from the mirror? Okay. When you go around turns, what happens to that thing that hangs from the mirror? Right? It swings one way or the other, depending on which way you turn. How much it swings is an indirect measure of how much acceleration you feel going around certain turns. Let's take a turn like you're getting off the highway, right? One of those big like loopy ramps that you kind of have to go around to get on or off the highway, right? As you go around that ramp, the thing that's hanging from your mirror will swing outward. How much it swing outward is going to depend on how fast you go. Okay? If you're going slower around that turn, it doesn't swing as much. Why? Because this acceleration depends on the speed. Right? If you go faster, it will swing out more. Faster turns require more acceleration. And specifically, what are we doing to the velocity in that formula for acceleration? Mathematically, what are we doing it? We're squaring it, right? So if you go twice as fast around the turn, how much acceleration is that? 4 times as much, because we're squaring that velocity. Now, let's take a different situation. Right? Instead of that big loopy turn that you use down the highway, let's talk about if you're driving down Hilliard and maybe you miss the turnoff if you go to your friend's house or whatever it is. Okay? But not to worry, on Hilliard, right, they have those beautiful gardens right in the middle of the road, so you can just make a U-E real quick, right? Not that you should, but you could. Even though you're going to take that turn much slower than we take the turn getting on or off the highway, you will probably see the thing that hangs from your mirror swing out pretty far. Because the radius of that circle that you're going around is much smaller than the radius of the entrance ramp to the highway. But where is radius in this formula? It's on the bottom, so it's inversely related, right? The centripetal acceleration, right? Doubling the speed increases the acceleration by a factor of 4. The acceleration is also inversely dependent on the radius. Having the radius doubles the acceleration. So if you go around a circle that's half as big, you're going to experience twice as much acceleration. All right. Good there? What do we need in order to accelerate? What causes acceleration? That's what acceleration is. Acceleration is a change in velocity. But what causes things to accelerate? Why do things accelerate? Changing speed or changing direction is how they accelerate, but what causes them to accelerate? Here, let me give you a hint. Gravity. Does this equation look familiar? Right? In order to have acceleration, what do you have to have? Force, right? If you are going to go around a circle, the first question that we did today, will an object go in a circle on its own? No. Circle is not a natural path. Things want to travel in a straight line. That means if you have a constant acceleration, you must also have constant force. And we call that force centripetal force. Centripetal force causes centripetal acceleration. So just like Newton's second law, right? F equals ma. So if you know the centripetal acceleration, you multiply it by the mass, that will then give you the centripetal force. And so it follows, if we take the formula for centripetal acceleration, multiply it by m on the top, we'll get centripetal force. So, key points here. How do I know? Key. Okay. During circular motion, the centripetal force has a constant magnitude of mv squared over r. That is the amount of force that you need to apply to get something to move in a circle. But the direction always directed towards the center of the circle. So it's a constant magnitude force, but it always has to be directed towards the center. In addition, the centripetal force is always perpendicular to the tangential velocity of the object in circular motion. Tangential velocity are those arrows that we were drawing on the original picture that shows you the speed and the direction.
Good afternoon, and pardon the interruption. Just a couple of announcements briefly.
Okay, so last thing. Because the force is always perpendicular to the velocity, it is not going to speed up the object. It is not going to slow down the object. It is only going to change its direction. It still causes acceleration, but it causes centripetal acceleration. Good there? Calendar. There are homework problems. These are conceptual problems, a couple of simple plugs and chugs. Then tomorrow we'll start getting into where does centripetal force come from?